Hey everybody, this is Mr. Murray back on Mr. Murray's Math Land, and today we are continuing solving trig equations, but this time solving what we call multi-angle equations, and that is when, notice this in the equation, when you've got some coefficients on the inside of your trig function. So your argument is not just x, it's something like x over 2 or 3x or 2x, something like that, and that is going to affect your solutions, of course. So we're going to see how that happens today. One thing you might notice if you remember your graphs, which we'll look at in a minute, is that affects the period of the graph. Period of a function, these trig functions, is normally 2 pi, and that affects that period, the length of the cycle. But if you don't think like that, that's okay. We're going to get right into it and see how we handle this anyway. Okay, so solving cosine of x equals negative root 3 over 2. One thing you might do, if this is your first one, is you might just say, you know what, I don't like that x over 2 being there, so let me just, let something stand in its place. Just so I can see something a little bit more normal, let me just call this like cosine of u, kind of like cosine of something equals negative root 3 over 2. Now it's looking a little bit more like the equations you've solved. Cosine of x, cosine of theta, cosine of u equals negative root 3 over 2. And at this point you should be thinking of your unit circle values, your circle, your chart, your triangles. If you need a little refresher on that, here are your angles, 30, 45, 60, or in radians as we're going to answer since they didn't specify, so that's kind of our default at this point. Pi over 6, pi over 4, pi over 3, sine, cosine, tangent. And remember these values, sine and cosine are all over 2, 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 root 1, root 2, root 3, right in order, and then backwards, root 1, root 2, root 3 for cosine. Sine divided by cosine gives you tangent. That becomes root 3 over 3, that's 1. Root 3 divided by 1 is root 3. So there's your values back in a hurry. Okay, so now, solving this equation, cosine of u, or something, is equal to negative root 3 over 2. So don't forget your trig quadrants here. All students take calculus, or whatever you want to call it here. Where is cosine negative? Cosine is negative in quadrant 2 and quadrant 3. So you would be saying, okay, I'm going to have two solutions between 0 and 2 pi for this. It's a reference angle. Cosine is root 3 over 2 for a reference angle of pi over 6, but I have to put it in quadrant 2 and quadrant 3, right? So you should be able to dial these up pretty quickly at this point by the time you get to solving these kinds of equations. But this would be your thought process, right? So u, or theta, or whatever, would be the quadrant 2 pi over 6, which would be 5 pi over 6. And your quadrant 3 solution would be 7 pi over 6, right? Pi minus pi over 6 and pi plus pi over 6, or 1 less than the denominator, 1 more than the denominator. And notice for these that it did not specify over the interval of 0 to 2 pi, as often it does. It didn't specify any interval, so that implies we want all of the solutions. So all of the solutions would be these first two, these initial two between 0 and 2 pi, but then plus 2 pi n, where n would be any integer, because you can just add that period or subtract that period if n is a negative integer, and that gets all your solutions. So if you are having trouble visualizing what I'm saying, here is the cosine graph. This is, as you can see, this is the red function there, y equals cosine of x. And I've shown two full cycles, so you can see it goes through that cycle between 0 and 2 pi. And from 2 pi to 4 pi goes through another cycle. And when we graph this, y equals negative root 3 over 2, which is where we just kind of solved this. Notice it equals negative root 3 over 2 at 5 pi over 6 and 7 pi over 6. And then it strikes it at two more places, which is 2 pi units later at 17 pi over 6 and 19 pi over 6. and so on and so forth. I keep, scanning out to 6 pi, and it's going to hit 2 more times, but it's just going to be that 2 pi units away. But okay, so here's the thing. U, remember, was standing in place of x over 2. So that's where we're going to now substitute this back in and say, okay, U was just kind of representing x over 2. And now how do we take what we have so far and find what we're really looking for? And just so you can visualize a little bit, when we graph cosine of x over 2, right, that's going to change the period to 2 pi divided by 1/2, which is really just going to give you 4 pi. And so when I take away that red graph, here is your graph of cosine of x over 2, and you can see now that period is 4 pi. So the two new solutions are 5 pi over 3 and 7 pi over 3, which we're of course going to obtain algebraically by taking our original two solutions here, and I'm going to multiply everything by 2 to solve for x. But I always like that visual on the first type of problem I do, so you can kind of tie it back to your graphing properties and see what you're really doing. And so anyway, to solve for x, we're going to multiply everything here by 2, including that period, because that's now 4 pi. And so you see that comes right along. So x is equal to 5 pi over 6 times 2 is 5 pi over 3. 7 pi over 6 times 2 is 7 pi over 3, and those were the two we saw on Desmos. And then plus 2 times 2 pi n is 4 pi n. And so I'll just slap some brackets around those two to show that each of them, if I were to add 4 pi n to them, I get my solutions. And there we go. We can bring that graph back out now that we've solved, and you can kind of see maybe that, hey, that period is 4 pi. Those are the two solutions. If you add 4 pi to it, you'll just get to these two right here, right? And then you could keep going and so on and so forth. Okay, but once you kind of trust that process, it's really that easy. So to summarize, find those initial two solutions between 0 and 2 pi plus 2 pi n, and then solve by multiplying by 2 or doing whatever it is to solve for the x. Okay, let's try a couple more though, because these can be a little tricky. Once you get the hang of them, no big deal. So sine of 3x is equal to root 2 over 2. So now I'm going to, rather than actually take the step of like letting u stand in place of this, I think by this point you kind of get the idea. You can start to say, look, I can't divide by 3 until I deal with the sine. So think about, when does sine equal root 2 over 2? Okay, so sine is positive root 2 over 2. Sine is positive in quadrant 1 and quadrant 2. And sine is root 2 over 2 for a reference angle of pi over 4. So our quadrant 1 and our quadrant 2 are pi over 4 and 3 pi over 4. And to find future solutions, I would be adding 2 pi n normally, right? And so now I'm going to solve for x by dividing by 3. Divide by 3, divide by 3, including dividing that 2 pi n by 3, because you see what that's going to make? 2 pi over 3, which is in effect your new period of this function. So you're just accounting for that. So my solutions, my initial two, are pi over 4 divided by 3 will give you pi over 12. 3 pi over 4 divided by 3 will give you 3 pi over 12, which does reduce, but I'm going to hang on to that for just a moment and leave it as 3 pi over 12. And now I'm going to add 2 pi over 3n to it. And if it just said solve, I would pretty much be done, except now it says solve over this interval 0 to 2 pi specifically, which means you have to find all the individual values in this interval. So I have the first two right here, where I finally solved for x after I divided by 3, but to find the others that are in this interval 0 to 2 pi, I I have to actually add 2 pi over 3 to each one of them. Okay, so 2 pi over 3, I want to think of that as a common denominator. 2 pi over 3 is equal to multiply by 4, that's 8 pi over 12. I have to actually add 8 pi over 12 to each one of these solutions. So we have the first cycle solution is pi over 12, 3 pi over 12. Add 8 pi over 12 to that, to each one of those, and you get 9 pi over 12. Add 8 pi over 12 to 3 pi over 12, and you get 11 pi over 12. And that will be the second cycle. And if you haven't, if you're a little rusty with your graphs, this means you're really going to go through 3 cycles within this 0 to 2 pi, because your period is 2 pi over 3. So you're going to get through 3 full cycles. So you really should have 3 rounds of solutions, if you want to call it that, 3 cycles of solutions. 2 in the first cycle, 2 in the second, and I'm going to add 8 pi over 12, the same period, the same 2 pi over 3. Keep adding it to find those actual values. Add that to 9 pi over 12, you're going to get 17 pi over 12. Add that to 11 pi over 12, you're going to get 19 pi over 12. And if you're thinking like, man, if I just keep adding it, I can keep getting infinite solutions. If you get a little carried away, notice if you add 8 pi over 12 again to 17 pi over 12, you'll get 25 pi over 12. But that is bigger than 2 pi. And same thing if you add that to 19 pi over 12, you're going to get something bigger than 2 pi. So you're outside of the interval. So it's kind of nice to trust that if it's 3x, for example, you're going to get through 3 rounds of solutions, 3 cycles. 1, 2, 3. You're going to have 3 times as many as you had initially. So now just make sure to actually write your solutions here. I'm going to kind of summarize and reduce all fractions. So x is equal to pi over 12, 3 pi over 12, which reduces to pi over 4, 9 pi over 12, which reduces to 3 pi over 4, 11 pi over 12, doesn't reduce, 17 pi over 12, and 19 pi over 12, all of which are less than 2 pi, none of which reduce. Check it out on Desmos if you like. Set your window to 0 to 2 pi, and you'll see those 6 solutions. Okay, one more, but hopefully you're getting the hang of this idea here. But just trying to show you enough of the twists and turns that can pop up here. So this is another one where we are solving 0 to 2 pi, so we got to actually add that adjusted amount, that adjusted period, if you will. And you have tangent of 2x is equal to 0. So, first, again, you got to deal with when does tangent equal 0? When does tangent equal 0? And if you're a little rusty on that, remember, tangent is sine over cosine. So when you're saying, where does that equal 0? And I guess this would be sine of 2x, cosine 2x. When does that equal 0? You're really setting the numerator equal to 0, right? You're thinking on that quadrantal situation. When is the sine value 0? And that happens 2 places, right? That would be right here where the y-coordinate 0. That would be at 0 degrees or 0 radians. Or right here at pi. It's the other spot where the y-coordinate or sine is 0. That would be a pi. And then, of course, back here, which is, 2 pi is coterminal with 0, but we're not including 2 pi. So you would normally kind of start this as saying, okay, this is equal to 0. The 2x is equal to 0 when 2x is equal to 0 or pi. Right? That's when tangent is 0 at those 2 angles, and you would add 2 pi n to those to describe future solutions. And so now to solve for x, divide by 2. So divide your solutions and your 2 pi n by 2. And you get x is equal to 0, pi over 2. And 2 pi n divided by 2 is pi n. And if you were to ask to describe all the solutions, you'd be good, you'd be done. But now you've got to actually add that amount to each one of them. So, because we want all the solutions between 0 and 2 pi. and none of the ones outside of it. So actually add pi, that adjusted period, to each one of these. So 0 plus pi is pi over 2 plus pi. It's a pretty easy fraction to do in your head. That's 3 pi over 2. And notice if you add it one more time, you'll get 2 pi here, you'll get 5 pi over 2. But those are both 2 pi or bigger, which we're not including in our interval. So these are our only solutions. And again, notice because it was 2x, you kind of had 2 cycles or 2 rounds of solutions. 0 to pi over 2, and the next cycle of pi, 3 pi over 2. And you can always check your solutions by plugging back into the initial, original equation, make sure it's true. That's always a way you can check and convince yourself, but you don't want to have to always do that. It can be time consuming. So there we go. There's 3 different examples showing you those multi-angle equations. Just a little bit of a twist on what you already know about solving equations. You got any questions, please ask. Hang in there and keep working hard.